Thank you, Costas. I'm without my beard, which is the way you would know that I was Neptune. Before I get started, I want to thank the organizers and the staff as well for a magnificently run conference. The selection of speakers was excellent. Everything ran as smooth as, from my point of view, ran as smooth as glass. I think that we should sort of collectively thank these folks. And I want to add my personal remark that IMPA is one of the places that I most enjoy coming to do mathematics in the whole world. I feel utterly at home here. I mean, after all, the coffee is wonderful, the working environment is fine, the library is excellent, colleagues are friendly, the staff is outstanding, and you have this beach down the way that's somewhat attractive as well. So, okay, this is, so I'll now get to these rogue waves that Neptune made. Actually, this trident has been replaced by other things, and we're going to try to find out what those things are. Okay, so this is joint work with Jean-Claude So. Everything I say here is joint work with him. Okay, now, so rogue waves started off as a term in oceanography, oceanographic. And you can find, I didn't bring along the written record, but you can find 200-300 years ago records by sailors talking about what we would now call a rogue wave. Waves, you know, that were 4 or 5 stories high that would swamp boats and so forth. Now, as far as I can tell from reading literature at that time, nobody believed this. I mean, the folks who sat on the land did not believe. They thought this was a fish story. You know, the fish got away. But, of course, nowadays we have ways of recording these things. And so it becomes something that one begins to believe in. So notice this is a nice picture. This is deep water. Rogue waves occur in both deep water and shallow water. We'll see some of both. I want you to notice that we're not in a storm situation here. Right? This background sea there is just ordinary sea, but you see this rather large wave that's approaching this boat, and there's some guy who should be running sitting here taking pictures. I think I would be running, not taking a picture. Here's another. Okay, so this picture is taken from an oil platform, and you see a boat going into the trough of a rogue wave. So boats don't do very well when they get out of the water like that. They're very strong in some ways, but they're not meant to do this. Not built for that. So this is not a good thing to happen. This is a slightly later picture. And by the way, this is still from the same oil platform. The oil platform didn't do very well. You'll see a picture of that in a minute. These things. Let's see. This is still deep water. This is a nice picture of a rather large, what we call a rogue wave. We'll talk more about what they are in a minute. I just want to give you an idea of what we're dealing with, approaching a freighter. Now, these next few pictures are shallow water rogue waves. So this is not deep water. Okay, remember, deep and shallow have to do with the size of the wave compared to the depth. I mean, these waves are all big, but out in deep water, they're not big compared to the depth. They're small. Okay, so this is shallow water. Here's another shallow water picture, very nice one from an airplane. And that's a wall of water there. That's not a mountain in the background. Okay, so these are rogue waves. Now, the problem with the real live rogue waves in the ocean is that some of my friends in oceanography convinced the United States government to give them $1 million or so to go out and look for rogue waves. And so they did this off the coast of Chile because evidently there are lots of rogue waves there, and also the wine is pretty good. So they looked for several weeks. They flew out in an airplane and so forth, and they found nothing. They spent a lot of money. It's very hard to find a rogue wave if you're looking for it, just like finding a tornado. You can wait your whole life in a spot and never see a tornado. So rogue waves, we don't have a lot of real live field data. Oh, sorry, I'm ahead of myself. Let me show you some of the things that rogue waves do. This is an example of what a rogue wave can do. That's another example. That's an aircraft carrier. Airplanes took off from that thing. One wave did that. This is that oil platform that didn't do very well. All right, now, so let's go back to this field data business. This is more or less the only field data we have. This is a North Sea oil platform, January 1st, 1995. Happy New Year. And here you see they had instruments in the water, and a rogue wave came along. So you see 5-meter waves. It's a fairly rough sea. This is deep water. Then all of a sudden you see something here, just one. Now it looks like 30 meters. In fact, it's probably more than that because the instrument saturates and you don't see the whole. I mean, it's not meant to measure waves of that amplitude. All right, so this is what we're dealing with. We're dealing with a situation where out of nowhere you suddenly get a big wave and then it goes away. So locally in space-time you have a large wave and then it's gone. Okay, so this is now lately, it is quite recently, people have found rogue waves in another environment where we have more control of what we're doing. Laboratory experiments become reasonable. And that's in the environment of fiber optics cables. So you know how this works. Let's see, let me show you. That's a better picture of it, in fact. These are thin filaments of glass. It's a special kind of, it's made in a very special way. And what happens is that you shine light in the end of it, generally generated by a laser, let's say. And here's the filament. And things are organized, the glass itself and the layers outside of it are organized in such a way that the light is trapped. It can't get out. It bounces around, but it can't get out. And so that allows the signal to propagate. That even allows signals to propagate if it's got a bend in it. Okay, you can actually propagate these light signals around bends. And you can propagate them quite long distances before they begin to come apart, and you have to collect it together and regenerate it. This is what happens. All right, so okay, this is a sort of a cartoon of the way these things are organized. Here's the part that matters. This is the glass. Each of those little ribbons has 24 fibers, so you're talking about an awful lot of information coming down the way. Remember, this stuff is traveling pretty fast as well. This has revolutionized communications, of course. Okay, and here's a picture showing you the way the light is confined. All right, now, okay, maybe I won't. I was going to tell you about the experimental apparatus, but I think I won't because of time. Here's an example of what folks in this end of thing are calling rogue waves. Now, you have to be very careful about what's going on here. What's happening is that there's a laser over here, and it's generating light pulses, and it's meant to be generating them more or less periodically. In fact, there's jitter. I mean, these things are going. You know, the frequencies are incredibly high, and so there's a fair amount of jitter. So what's coming in to here? Sometimes they model it stochastically. It's a boundary value problem. It's not an initial value problem. The boundary value is here, and then they make some measurements over here. The spectral measurements, what they're interested in. So this problem, you'll see how it gets modeled in a little bit. But here, since it's a laboratory situation, we have the possibility of doing experiments. And so I think we've learned something about rogue waves in the ocean from what's going on here in this very microscopic environment. Okay, now, the question that I want to be concerned with is, where do they come from? In other words, what generates a rogue wave? In the case of fiber optics cable, if you understand that well enough, you might be able to control these large signals, which you don't want, by the way. In the case of the ocean, I don't think we're going to be doing much controlling, but at least it would be interesting to know why. So there are various theories available. I'm now speaking about the water wave context. One theory is concurrence of various types. Roughly speaking, concurrence just means that the ocean is big, you have energy everywhere. It may not be very big, but it's all over the place. And maybe, it could get together and have a party, and you get a big wave. Okay, so there are various versions of that, which I call concurrence. It's just coalescence of a lot of energy, sort of perhaps by accident, in a small area of space-time. That one, by the way, is attractive because what it means is that the wave will be big for a while and then it will go away. It will not be like a tsunami. Tsunamis, keep right on propagating for thousands of kilometers. Rogue waves don't do that. They get together and then they seem to come apart. They go away. I mean, you see them one place and then where you might expect them to have been later, it's not there. Okay, so that might fit, concurrence might fit at least that aspect. There's another idea, which is a sort of a statistical theory of wave amplitude, which says that wave amplitudes, this is amplitude along here, this is frequency of them up here, they follow some kind of distribution like that, and way out here are big waves. Okay, there's papers that say things like that. This is not very satisfactory because, of course, what you want to know is what generated that curve in the first place. Another idea is wave-current interaction. So this would be a situation where you have a current going one way, waves coming the other, possibly wind-generated, and you might get big waves that way. There's some evidence that might be an idea. And, of course, in shallow water, it could be topographical forcing. Deep water, that wouldn't apply. But in shallow water, it could be a situation where waves get focused by the underlying topography. If it's shallow water, the waves feel the bottom, and they can be directed, they can be diffracted. All right, so these are the ideas. Now, oops, sorry. Yes, I'm going to be concerned today with concurrence. Okay, so the question I have in my mind is concurrence a possibility within the context of water wave models? This is a mathematical question. You can ask the question. And by the way, if the answer is no, then you rule this one out as a possibility. If the answer is yes, this does not mean it's what happens. It just means it's still possible. It's still on the board. All right. Now, the idea of concurrence, this is a little cartoon. You mustn't take it seriously. The idea here is that I want to start with, say, an initial value problem, and you'll complain right away that my fiber optics cable wasn't an initial value problem, but the physicists turned it into one very quickly, you'll see. So you construct initial data, which is small, everywhere small, but I'm talking about all of R2, the whole ocean, unbounded ocean, so there's energy everywhere, and I'm going to organize it in such a way that so I'm going to use dispersion. And the way I'm going to use dispersion is that different wavelengths travel at different speeds. And so I'm going to place my energy in a clever way so that it all comes together at one point in space-time and makes a big wave. That's a very simple idea. The question is, can you really do it or not? All right. Okay, I'm going to start with the very simplest model that you can think of in this context, which is the linear Schrodinger equation. That's not a bad place to start. First of all, it has directly, as you'll see, has directly to do with the fiber optics situation, and with appropriate changes, which I'll mention later, has to do with the deep water situation for water waves. So this is a reasonable place to start. And by the way, it's very simple. So we can solve that problem. Take the Fourier transform in the spatial variables, solve the little ordinary differential equations, take the inverse Fourier transforms, just like the heat equation. There's the solution. Okay, now, what's the idea here? I want to choose for the time being, let's just focus on choosing initial data phi. I want it to have finite energy. Okay, so finite energy, that means it needs to be an L2. Okay, D is equal to 1 or 2 here. The dimension, from the point of view of physics, is 1 or 2, but one doesn't need to restrict oneself at this point. So you want it to be here. You want it to, of course, be in L infinity, let's say bounded and continuous. And you might want some other properties as well. Okay, I want nice initial data, nicely bounded, and I want it to get big in finite time. It's a linear problem, okay, just a linear problem. All right, so it's actually easy to design such data. Here, this one will work. Okay, I'm taking advantage of the dispersion, you'll see. Here, let's go back and put this on the board. What's the solution with that initial data? The solution is u of xt is 1 over 4 pi I t integral over rd e to the minus I x minus y squared over 4t e to the I y squared 1 plus y squared to some power. Right? I think I got all that right. Sorry. No, I didn't. Now I got it right. Okay. So that's the solution of that problem. Okay, now remember I want it to be, by the way, that's a C infinity function. It's smooth, so there's no problem about the question of smoothness. It's bounded. It's obviously bounded for m positive. And you just check quickly if m is bigger than the dimension over 4, it's an L2 function. Okay, so let's assume that. Let's assume that m is bigger than d over 4. And now I've got myself initial data, which is in the right kind of class for me. And there's the solution. And what could be the problem with the solution? Well, you see it right away. If you take x equals 0, so mark this one out, and you let t go up to 1, right, all the oscillation, which is what makes this thing smooth, this is a smooth function, except when all the oscillation cancels. Right? When x equals 0 and t equal 1, not t equal 1, t equal a quarter, so at the point 0, 1/4, all the oscillation cancels, you're just left with this. Okay, m's bigger than d over 4, but if m is further restricted to be less than or equal to d over 2, that blows up. Right? That's plus infinity. Maybe, oh yeah, there, okay. Right? That thing will blow up. And so there's if I choose m in this range, I have a chance of getting the kind of thing I'm looking for. A solution that starts out life nicely bounded, which gets very large in finite time. Okay? Now, this is linear. The problem is linear. So, I mean, I could multiply this by this data by delta. Any small positive delta will do. And I'll have data which is not only small, it's really small. Delta could be 10 to the minus 50. And yet it'll still get, you can't see it, and yet it'll still form a singularity in finite time. Okay, now you can, okay, then there's some mathematical work to do now to show that this thing is a nice bounded function away from the one point where it goes wrong, and that it does actually blow up, not just formally, but actually. Okay, that's elementary stuff. Okay, now let's see. Some remarks. This result is self-improving in several ways. Okay, so one way it's self-improving, after all, it's a linear problem, I could add up a bunch of these. Right? I can take this initial, I mean, by the way, this point 0 1/4 is, there's nothing special about that. Any old point that I chose in the upper half plane could have been the point where it blows up. You just alter things a little bit and you'll get that. And so if I want, in fact, if I want the thing to blow up, here's x, and here's t. If I want it to blow up at a bunch of points in the upper half plane, I just add up a bunch of these things with appropriate weights, and I get myself another function which lives in classes like this, which blows up at all those points. Okay, so you can have it blowing up at a bunch of points. Okay, now one of the first things you'll object to about this as a description for possible rogue waves in the ocean is that I've had to organize the data in such a specific way that you just can't imagine this would ever actually happen in the ocean. But it's not that bad. You see, suppose we work in dimension d equal 1 for a minute, just to be concrete. Okay, so suppose I take this initial data, this special initial data phi that I had, and I add on to it some h1 initial data. So u0 is just an h1 function. Well, this one stays bounded forever, and this one blows up just as it did before. So all of these solutions have singularities. Okay, well, maybe you don't like the fact that this function phi is not in h1. Of course, it couldn't be. If it was in h1, it wouldn't blow up. Okay, so that's all right. You can cut it off. Take some sort of cutoff function, say x over r, multiply it by something small. Okay, now it's a h infinity function, smooth. All derivatives are in L2. All of those, they don't blow up, but they get large at this point that we're talking about. And they start as small as you like. Right? The delta is under your control. They start as small as you like, and they will get as large as you please. This depends on your choice of r at a finite point. Okay, so the point I'm making is that this phenomenon that we've just discovered is more robust than you think. Okay, there's more. Okay, and this is something I won't come back to this over and over again, but all the way through the lecture, this aspect is underlying things. In other words, it'll look like I'm doing something very special. It's not nearly as special as it looks like. All right. Now, okay, so this is just what I said a minute ago. Oh, yes, but this is just for fun for people who like these kind of things. It's actually a little bit of a mess to show that this thing is nice and smooth away from the blow-up point. There's some little bit of analysis to do. If I take t equal to a quarter, and I look at what this thing looks like exactly at t equal to a quarter, that's when 4t is 1. In that particular case, it's a Fourier transform of Bessel potential, and you can actually figure out what it is. There it is. It's a Bessel function of second type or whatever it is. This thing k has a singularity at the origin, but it's C infinity otherwise and decays exponentially to 0 at infinity. So this is what the thing looks like just at that critical time. All right, I probably shouldn't do this, but I'm going to show you how to do it in higher dimensions. Okay, so in higher, this is the way you tackle this problem altogether. This is the integral I that you care about. The rest of it is, t is about a quarter, and x is something in the real line. There's no trouble with this term. It's the integral that might have trouble. So the integral is over RD. You break it up into the integral over the ball and the integral over the rest. Integral over the ball is no problem. The Riemann-Lebesgue lemma tells you that's a continuous function, goes to 0 at infinity, etc. And so it's this one, what I call I2 here, that it's interesting. Take t not equal to a quarter so that beta here is non-zero. Okay, alpha and beta depend on t, and let's just look at the case where t is not a quarter. If t is a quarter, you have to do something a little different. All right, and then what you do is you change variables. You use polar coordinates, and you write it as an integral over the sphere and an integral over the with respect to r. And because beta is non-zero, you can integrate this by parts, and that's the way you show the thing is a bounded continuous function, away from t equal to a quarter. T equal to a quarter, as I say, something else, you do something else. Okay, so this, by the way, is what happens all the time. Now, what happens, okay, this is all linear. What happens if it's a nonlinear problem? Because after all, waterways are not governed by the linear problem. So let's, okay, I work in one dimension. And I want to solve iut plus uxx plus u squared u is 0 with initial data. And, well, I'm going to use the de Hammel formula to get a representation. So the solution will look like the linear semigroup on the initial data plus the de Hammel term. Okay, maybe possibly I wrote all that down. Oh, sorry. Should have. I did this for the Schrodinger equation. That's actually not deep waterways. That's okay for the fiber optic cable. It's not deep waterways. Deep waterways, you have this sort of hyperbolic version of the Schrodinger equation. The analysis is the same. You don't notice the difference. Okay, now here comes the nonlinear problem. Have my mathematical hat on here. I put a P there. P equal 2 is what you care about, of course, in almost every physical environment that I know of. But we can have other values of P. So here's this de Hammel representation. This is the problem we just analyzed. Right? That's what we just did. And then there's this de Hammel term. So if I wanted to show the same kind of dispersive blowup for the nonlinear problem, all I would have to do is take this special initial data that we've already designed, put it into the problem, and show that this term is bounded and continuous. Right? If this one is bounded and continuous, this one we know what it does. It blows up at this point, whatever point we selected. So that means the solution will blow up there too. Right? I mean, this is not the usual way of things, right? Normally it's the nonlinear term that's making things blow up. But here it's the linear term that's going to make things blow up. And the idea is to show that this thing is nicely bounded. Okay? And this is just Strickhart's estimates. In the Schrodinger case, this is not hard. Strickhart's estimates will tell you that this thing is bounded for the type of data that we're talking about. Okay? So the nonlinear problem has the same... sorry, there's a restriction here. I beg your pardon. This works for 1 less than or equal to p less than 3. Beyond 3, we're not so sure. Okay, but anyway, p equal 2, which is the one we care about, is in that range. So. All right. Now, let's talk for a moment about these optical Roadways. So, unfortunately, it's nothing so simple as the Schrodinger equation. It's a Schrodinger-like equation. Here it is. And you have to be very careful here now, because I'm writing this as a mathematician would, dA dt, and I'm using z as the spatial variable. This is one space dimension. This, in fact, remember, it's a boundary value problem. It's not an initial value problem. And what the physicists have done when they get to this point is they've traded space and time to turn the boundary value problem into an initial value problem. Okay, so you have to be very careful when you start interpreting the results, what you're doing. The initial data is actually boundary data. Okay, and there's a very interesting question about how good is this? Is this a good idea or not? I don't know the answer in this circumstance. I do know the answer in the water wave problem. The answer is no, it's not a very good idea to turn initial data into boundary data. The error you make when you do that is the same order as the correction terms to the basic wave propagator. So it's not a good idea. Okay, but in this case, I don't know whether it's good or not good idea. I haven't checked. However, this is what the physicists do. Now let me explain. This is a damping term. That is the dispersion relation. And they write it as a Taylor series. way they write it. This is what's called a response function. The R is the response function. There's 2 bits to it. There's a delta function. That's sort of the local response. And then there's this H term, which is the Raman effect. This is a delayed effect that occurs. Okay, and this is their way of modeling it. Okay, now, if this term T shock is 0, of course, this feels a lot like just ordinary Schrodinger, and you can analyze it pretty easily. If this is not 0, then you've got a derivative here. You're losing derivatives. You're losing smoothness. And what you need to do is a little more complicated. And in fact, I won't go through it because I'm going to do it for the Korteweg de Vries equation where the same thing comes up. All right, so this, okay, I'm concealing an enormous amount of work right now. Preliminary fussing around. So this is scaling, changing the dependent variable to get rid of that damping term, truncating the Taylor expansion. And by the way, when you truncate the Taylor expansion, you have made a presumption about what wavelengths you're concerned with. That's how you decide where to truncate. And a perturbation argument on top of everything else gets the issue down to just this. If you can handle this, then you can go back to the original problem and you'll understand it. Okay, now the choice of k, of course, is important. If k is equal to 2, then we're back to the Schrodinger equation that we just analyzed. We have this under control. If k is equal to 3, we're at the Korteweg de Vries equation. And Strickhart's estimates are not good enough for that. That's not, you have to do a little bit more work. We'll talk about this in a minute. Higher values of k might conceivably come up here. Okay, the going will get harder as you get as it gets higher. You'll need to use the higher order smoothing effects for the Schrodinger-like ones, and you'll need to use what I'm going to show you for Korteweg de Vries for higher order Korteweg de Vries equations. Okay, but I'm going to. Okay, now so let's now go to the. Now if I'm thinking oceanographically, I'm in shallow water. And now it's no longer the Schrodinger equation that's the right equation. It's the Korteweg de Vries equation. So let's do what we did for Schrodinger. Let's do the linear theory first. So there's the linear Korteweg de Vries equation. You take the Fourier transform. This is, of course, just one space dimension. You take the Fourier transform and solve. There's the solution. Take the inverse Fourier transform, and there's the solution. Okay? This is classical. It's really classical. Goes back a long way. This AI is the Airy function, and let me just remind you what that looks like. So the Airy equation, remember Airy derived this equation when he was doing his work on optics. It's just this little ordinary differential equation. And of course it has a two-dimensional space of solutions, and here's a basis for it. I'm just showing a picture. The red one is what's called AI, and the green one is what's called BI. It's not bounded. AI is the one we care about. There it is. Okay, now the asymptotics of that are important for us, and here they are. So near plus infinity, this thing decays super exponentially. It's got an x to the quarter as well, but that's not important. It's the super exponential that you're interested in. This thing goes down to 0 very, very rapidly. You can get a hint of that in this picture. On the other hand, near minus infinity, it still goes down like x to the 1/4, but all it does is just oscillate. It doesn't. There's not the decay rate is just 1 on x to the 1/4. That's it. Okay, you can see that here too. It's decaying, but not very fast. Okay. So of course this means that it's not an L1 function, or an L2 function, or even an L3 function. It's an L5, not in things below 4. All right. On the other hand, because of that oscillation, it has improper Riemann integrals, and the usual thing to do is to normalize it so that, so that integral is 1. Okay, that's the normalization you put in. And by the way, when you put that normalization in, that's when you get exactly this formula. If you don't have that normalization, there'll be a constant out here. Okay. Okay. Now, where will we get dispersive blowup in this case? And of course, we already know the answer. We're supposed to look for the dispersion relation. So there it is. Here's the phase speed for Korteweg-de Vries, and it's 1 minus k squared. Okay, so this is just like Schrodinger. The phase speed is unbounded. So that means that I can move energy around as fast as I like, and that probably means I've got a chance of having this dispersive blowup. So the short waves, that's large values of k, are the ones I can move rapidly. The long waves, of course, I sort of stuck with what happens to them. But the short waves I can move around very rapidly. So the idea is the same as before. But here we can be very specific about it. I want to construct data which has shorter and shorter wave components out near plus infinity, right? Because because they propagate in the negative direction, right? So I want initial data. Here's the idea: you take initial data, you put a bit of it down, then you go far down the channel and you put some more down, shorter wavelength, and then much further yet, the more. Of course, I need to have these things decaying so that I get an L2, I get finite energy. But you see what's going to happen. Say this is really long wave stuff, so it doesn't move very fast. This is shorter waves, maybe it moves like that. This is really short, it moves like that. And if I just space these things right, I can get them all to coalesce at one point in space-time and make this big wave. This is just what we did for Schrodinger. All right. So what I need is initial data. It's got short wave components out near plus infinity. And it's easy to find such initial data. Just take the Airy function and turn it around. All right. Now all the oscillation is out near plus infinity. Well, that's not an L2 function, but we can make it L2. Just divide it by a suitable power. And you've got yourself a nice L2 function. It's certainly bounded. It's C infinity. It's what we like. And here's the solution. Okay, and again, you see what happens. These two Airy functions oscillate like crazy. The cancellation is enormous. So this is a nice smooth function, except when x equals 0 and t equal 1, and all of a sudden it's Airy squared. There's no cancellation. Any other space and time, the cancellation is there. Okay? It's integration by parts. That's all that's involved. It's sort of a messy integration by parts, but you can do it. But just at those points, it doesn't work. And so, all right, so so you do the arithmetic. This thing is an L2 if m is bigger than an eighth. Okay? And you can easily check that. But this thing, remember, this is the kernel, this is what you're integrating exactly at x equals 0 and t equal 1. This thing is not an L1, not an L1 if m is less than a quarter. Okay, so if you take an eighth less than m less than or equal to a quarter, right, you've got initial data, which is finite L2 norm. And by the way, remember, right now we're at the linear level, as small as you like, which gets big at a point. And by the way, as many points as you want, countable number of isolated points in the upper half plane. And you can still do this trick that I mentioned before, and I won't keep on mentioning this, of turning it into smooth data, which gets big, maybe not blowing up. All right, so that's the linear problem. Now, certainly for shallow water, you don't believe the linear problem is telling you what's going on. In deep water, okay, one might wave one's hands a little bit, but in shallow water, you're sure that the nonlinear effects are very important, and one sees this in laboratory experiments. So what does the nonlinearity do to this? Well, we're going to do the same thing we did before. We're going to represent the solution in its Duhamel form, and the idea is we're going to take the initial data to be that stuff that I just showed you, that Airy function turned around with an appropriate weight, and we want to understand that this term stays nicely bounded. Okay, so let's see. All right, so here it is written out in gory detail. This is the term that I need bounded. Now, see, this is different from Schrodinger. Strickhart's estimates are not going to do it because of this loss of a derivative here. It's just not good enough. So at first, actually, when Jean-Claude and I were first working on this, we sort of didn't think we were going to get anywhere with this thing. But if you think about it a little bit, okay, now what I'm doing right now is just formal. So the initial data, let me remind you, the initial data here, eta naught, is the Airy function turned around divided by 1 plus x squared to some power. And the power has to at least satisfy those restrictions. All right, so this function, while I mean it's an L2 function, but it's better than L2. It has very definite decay properties. Okay, now near minus infinity, the Airy function, I've got it turned around. So for x near minus infinity, this thing is super exponentially going to 0. So there's no problem near minus infinity with any convergence. Only near plus infinity where you might have trouble. Okay, so let's just, looking at the data, eta goes down like that at plus infinity. Its derivative goes down like that at plus infinity. And the Airy function has a little bit of decay itself. Right? So if I would go back to this formula here, okay, I'm just talking about the initial data right now, but one can imagine organizing M in such a way that those various decay rates add up to something which is an L1. So bounded. All right, now can you do that? Well, okay, so here's the eta y times the Airy function. This is the decay rate that you get from the whole combination. And so if a quarter plus 4m is bigger than 1, you're in L1. Okay, and that's m bigger than 3/16. So that's fine. Okay, I can't go down to an eighth maybe, but I still have room here to choose an m where I have initial data that linearly blows up in this dispersive way, and where this term might possibly be bounded. Now, what's the problem? The problem is that all these calculations were at t equals 0, the initial data. So what? Okay, so now it's a technical point. Everybody in the room would see it instantly. You need to show that those decay rates propagate forward in time. You need to show that if you take initial data that satisfies decay rates like that, and you turn on the Korteweg de Vries equation, the nonlinear one, that this propagates those decay rates. Okay, and okay, that's hard work. I will not show you any aspect of it at all, but you can do it. It's not beyond your wit. Okay, so then once you've done it, you're in a position to find yourself initial data for which this term blows up at, say, x equals 0 and t equal 1, and this term stays nicely bounded. Okay, and so the solution blows up in this dispersive way. Okay, that's the way it works for Korteweg de Vries, and that's, by the way, what you have to do. Going back to the fiber optic situation, if the k is equal to 3 or 5 or 7 or 9, this is the kind of analysis you have to do. It's easier for the even values of k because then you're in Schrodinger type situations. Okay, so here's a theorem which I don't think any of your the conference has been long. Nobody's going to read this theorem, but it says what I just said. You can take initial data, which is in HK, and has a k plus 1 bounded derivatives, and that k plus first derivative can be made to blow up anywhere you want. Okay. All right. Now, all of these are model equations, and really you'd like to know about the real water wave problem. I mean, because if we're talking, I mean, for the Roadways in fiber optic cable, maybe the analysis is sufficient to leave on the table the possibility of this type of recurrence being an answer for why you see roadways. But for the water wave problem, deep water or on shallow water, I've made approximations that you may not be happy with. Okay, so, and there's another point. Both Schrodinger and Korteweg de Vries, I was relying on the fact that I could move energy around as fast as I liked. The phase velocities were unbounded, so I could move things as fast as I like. Now you might wonder, is that necessary? I mean, do you have to have unbounded group and phase velocities? All right, so let's go to the Euler equations, the linear Euler equations, 1 or 2 dimensions. Here's the dispersion relation. This is the full water wave, linearized water wave dispersion relation. The phase speed is not unbounded. And by the way, the group velocity is not unbounded either. So it's not clear that what we learned from Schrodinger and Korteweg de Vries is actually going to apply to the water wave problem. I mean, we learned some tricks, but we were relying on this unboundedness of the group and phase velocity. And this is certainly not unbounded. Okay. Now, this was an intermediate stage in our thinking. What we actually, one way to interpret what we showed for Schrodinger and for Korteweg de Vries is that they're not well posed in L infinity. You can start with tiny L infinity data, and it will get big in finite time. In fact, it blows up in finite time. Okay, they're not well posed in L infinity. This is something that people know, but maybe not quite so precisely as this blow up. And so that would be your first thought would be for the full water wave problem, say the linear one. You might want to show it's not well posed in L infinity. Okay, and you can do that using some old and rather deep work of Wenger and Miyachi. We can show directly, without doing anything special, that the water wave problem, linear water wave problem, is ill-posed in L infinity. Okay, but in fact, let me show you a little more about this. If you take the full Euler equations, two dimensions or 3 dimensions, and you linearize it around the rest state, that means flat top and no velocity, you can beat that into a much simpler problem. And here it is. Okay, it looks like the wave equation. Would be the wave equation if this was k squared, but it's not. It comes from the dispersion relation. There it is. Okay, from that dispersion relation you just saw. Okay, so this is the linear water wave problem. And okay, one would like to show that this is ill-posed in L infinity. You can do that. That's what I just said. But you can also show that it has dispersive blowup. Now the point of it is that the phase velocity here it is not unbounded. Right? This is bounded. It's, perfectly bounded function. If you let the depth go to infinity, you do get something that's unbounded. But for finite depths, you can solve this problem using Fourier transform. There's the solution. So this is, let's see, let's go back. No, I didn't seem to. Oh, yeah. You need 2 bits of initial data, of course, for this. So here's the solution of the problem. And you see these sines and cosines. This thing is well posed in L2 base spaces. Right? Any of your favorite L2 base Sobolev spaces, this is well posed. It's a triviality. But it's ill-posed in L infinity. And it does, in fact, have dispersive blowup. That is, we can find initial data which blows up in finite time. Let's see, I don't think I bothered to show you how to do that. The going gets a lot tougher than for Schrodinger and Korteweg de Vries. These methods can also be used on fractional order Schrodinger type equations. These types of equations come up in some turbulence models that Zakharov and his colleagues have put forward. And they also have dispersive blowup. And let's see, there was one more. Oh, yes. Okay, so the water wave problem, the full linear water wave problem has dispersive blowup, Schrodinger and Korteweg de Vries do, you might imagine that maybe all dispersive equations have dispersive blow-up. Maybe anytime you've got different speeds of propagation, you can do what I've been doing. Organize the initial data so that there are bits all around and get them to come together. It's something that would occur to you. And it's not true. There are dispersive equations that are well posed in L infinity. Yes?
A few minutes.
Am I finished? Okay, I promise to take only a minute. Let me show you one of these that's well posed in L infinity. This is like the Korteweg de Vries equation. It's this equation that Benjamin and Mani and I put forward a long time ago. That's well posed in L infinity. It does not have dispersive blow-up. Okay. The model that you would look at to try to understand where are the limits of dispersive blow-up would be this one. This would be a very natural one. So Jean-Claude and I make a distinction between weakly and strongly dispersive. And by that we mean, does it have dispersive blow-up? If it's strongly dispersive, it has dispersive blow-up. If it's weakly dispersive, it doesn't. And the cutoff here is lambda equal 1. So for lambda bigger than 1, this does not have dispersive blow-up. For lambda less than 1, it does. Okay, now this leads to a whole set of questions about, one would like to do this in higher dimensions and so forth. These are things we're working on, but I think I'll stop now because Kostas is very gently telling me I should. Thank you very much for your attention.